Hello G9. Okay, second video lesson. Still we are talking about magnetic field, so you can write topic of today's lesson, a motor effect. Okay, motor effect is strongly related with magnetic field and of course with electric field. Okay, a short revision of our last meeting, of our last lesson. We are talking about magnetic field. You know that magnetic field is a region or space when something called magnetic force acts. Yeah? So if you know that object experiences a force and the nature of this force is a magnetic force, then it must be placed in the region of magnetic field. Is that clear? Okay. Second, you know that magnetic field can be represented by field lines. Okay? And I've created few examples related with this subject. You've created field lines around typical bar magnet, field lines around two magnets, field lines around broken magnet, field lines around the earth, etc., etc. And what is the meaning of the field line? If you know field line and any space, okay, then field line shows us orientation of bar magnets placed at this space. And remember that field line always starts at the north pole of the magnet and goes to the south pole of the magnet. And so field line represents something like a position of magnetic objects, or other words, magnetic objects or magnetic poles are orientated along field lines. Is that clear? So this is something we did in our last lesson. Okay, today we will focus on something a little bit different, connection between electricity and magnetism. Probably you've heard the term electromagnetism. Okay, in physics, these two phenomena are very strongly related. Yeah. First example: each moving charge creates a magnetic field. Each change of magnetic field creates a change of electric field. So basically, electric field creates a magnetic field when it changes, and vice versa. So this moving change is known as an electromagnetic wave. We were talking about electromagnetic waves. Okay, so electricity and magnetism are strongly related. So usually physicists use the term electromagnetism. Okay. Okay. So what is a motor effect? First of all, I hope you are prepared to the lesson. You have books, notebooks, pencil, pen, ruler, eventually calculator. Okay? So let's look. Let's imagine that you have a current through which a wire through which current flows. Okay? So what happens with this wire when it's placed in the magnetic field? It experiences something like a magnetic force, because, as I said, there is a strong relation between electricity and magnetism. Okay, so write point number 1. When a current, when a wire through which current flows is placed in the region of magnetic field, then it can experience, okay, a magnetic force. Okay, I wrote can experience because there is one more condition, but about condition later. Okay, so please copy this. If the speed of talking, of writing is too fast, of course you can stop the movie and turn it again later. I'm going to the next point, to the point number 2. Okay, this magnetic force depends on And we have few factors influencing the value of this magnetic force. First of all is the strength of the field, because if field is stronger, then a bigger magnetic force acting on this current carrying wire. Okay? So strength of the magnetic field. And as you know, magnetic field is represented by letter B. Okay? Strength of magnetic field B. Second, current in the wire. Okay, current has a symbol of I. If bigger current flows in the wire, then stronger the magnetic force, of course. And third, the length of the wire in the magnetic field. In the magnetic field. I'm going to use letter L like length. Okay? And there is one more factor. Because all depends also on the orientation of the wire in the magnetic field. So maybe orientation or angle between the wire and the magnetic field lines. Okay, and I'm going to explain only the last factor here, because the rest will be on next slide. So let's look. If you have a wire with current placed along field lines, okay, then no magnetic force. Magnetic force is equal to 0. It's very, very, very important. Okay? If wire is placed perpendicularly to the magnetic field lines, then the magnetic force is the biggest possible. Okay? And you are not interested what happens if there is angle which is different than 0 or 90 degrees. Okay? You must know that if there is a right angle, then force is maximum possible. If current carrying wire is located along field lines, then there is no magnetic force. Okay? Stop video for a moment, copy this to your notebook, and when you will be ready, turn it back, and point number 3. Okay. Point number 3 will be direction of magnetic force. And this is the most important part today, because what does a motor effect mean? Motor effect means that something moves. So basically, when a current carrying wire is placed in the region of magnetic field and magnetic force acts on the wire, then it moves. Is it clear? And this effect is known as a motor effect. So the movement of current carrying wire in the region of magnetic field. But how does it work? Let's imagine something like this. It's a quite difficult topic because all happens in third dimension. Let me draw and then I will explain or try to explain. Let's imagine that you have magnets. One magnet which is located to the left. Again, this is three-dimensional picture. I hope it's visible. And let's imagine that here is the north pole of the magnet. And second magnet which is located to the right. And this is south pole of the magnet. So there must be a magnetic field between these two magnets. I'm going to use red color to present magnetic field in the form of lines from N to S. I hope that you remember that field is from north pole to the south pole. Yes, from north pole to the south pole. From north to the south. From north to the south. Is it visible? I hope. Yes. Tell me yes. Yes. Okay. One more and one more. So again, north pole of the magnet produces lines and south pole of the magnet takes these lines. Magnetic field is directed from north to south. Is it clear? Okay, let's imagine that inside this field you have a wire which lies perpendicularly to the field lines. Again, this is three-dimensional picture I hope that you see the orientation of this current. Let's imagine that you are observing this situation from this perspective, from the perspective of wire. What you see? I'm going to create exactly the same situation, but in 2 dimensions. To the left you see North Pole, to the right you see South Pole, and magnetic field lines which are directed from left to right, from N to S. Again, left picture is 3-dimensional, right picture is 2-dimensional for people who don't perceive 3 dimensions. Okay, and wire which is directed towards the screen. From this perspective, from the perspective of this eye, wire is directed towards the screen. Is it clear? Okay, so this part of the wire, let's say from this to this, is placed in the magnetic field, so I'm going to mark this part by letter L, length of the wire in the magnetic field. Okay, so let's look. We know that in this particular situation, magnetic force must act. Why? Because wire makes 90 degrees with the magnetic field lines. Or other words, wire doesn't lie along field lines, which means that magnetic force acts. What is direction of this magnetic force? To find the direction of this magnetic force, we have to use something which in physics is known as a Fleming's left hand rule. You have to take your left hand and make something like, let me try to draw, like this. This is your thumb. Yes, I know, beautiful picture. This is your first finger, a pointer. Oh, not bad. And this is your second finger, middle finger. My middle finger is a little bit better. Okay, so you have to make 90 degrees between your thumb and first finger, and 90 degrees between your first finger, this is first finger, yes, and the middle finger. I hope it's visible. Yeah, this is your thumb. Okay, and rest finger, we are not interested what happens with rest fingers, so rest fingers lie here. The third finger and the small finger. This is the third finger and this is the small finger. Oh, not bad? Not bad. Try to copy this. Yes. Yes, I see first finger is too fat compared with others, but I think the idea is clear. Okay, few lines. I have lines on my head, on my hand. Sorry. Here I have a different line here, something like this. Yeah, nice. Okay, so by using this sign, let's name it sign, you can state direction of the force. Let's look. Thumb represents direction of force, F. First finger represents direction of magnetic field lines, B. Middle finger represents direction of current carrying wire, I. So it's easy to memorize. You can imagine that this configuration of your fingers presents something like a pistol, but of course left hand, not right. And you can imagine that you have a pistol and you say FBI, freeze. It's easy to memorize. FBI, F, force, B, magnetic field, I, a current. Okay? Of course, all three lines make 90 degrees. So B makes, let me make this line more straight, B makes 90 degrees with F, which makes 90 degrees with I. You see? F, B, I. You have something like three-dimensional coordinate system, and you have 90 degrees between this and this, 90 degrees between this and this, and 90 degrees between this and this. Which one? Between FB, between BI, and between I and F. So between I and F. So here is also a right angle. Oh, Okay, so now let's use this rule and try to find direction of force, of magnetic force acting on this current carrying wire. Okay, so or here will be a little bit easier. Okay, so let's take your left hand. Okay, and let's move it in such a way that B, your first finger, is directed to the right, from N to S. Okay? Current, so your middle finger is directed towards the screen. So you have to turn your hand. So what is direction of thumb? In my case, the direction of thumb is down, which means that current experiences a magnetic force directed down. This force is perpendicular to the direction of current and moves or pushes current carrying wire down in the same direction as gravitational force, but accidentally. Okay, so in this particular example, magnetic force acts on the wire because wire doesn't lie along field lines and is directed down due to this left hand rule. Okay? Please stop video for a moment, copy this to your notebook. Yes, I know it's difficult, but you can copy this hand from internet. When you write Fleming's left hand rule on Google Images, then you can find it. Copy this to your notebook, and when you will be ready, next slide. Okay, so as a conclusion of today's lesson, what is a motor effect? Motor effect means that when current carrying wire is placed in the region of magnetic field and doesn't lie along field lines, then it experiences a force which moves it. Is it clear? So motor effect means existence of magnetic force. But remember, magnetic force acts on the wire only, magnetic force acting on the wire, only if wire doesn't lie along field lines. Okay? So wire cannot be parallel to the field lines. Okay. How to find direction of magnetic force? Direction of magnetic force is related with left hand rule. I'm not going to repeat the picture again, but remember, you have to make FBI sign. Okay? And magnetic field, the strength of this magnetic force, or magnetic force, the value of magnetic force, depends on few factors: on the strength of the field, on the value of the current, on the length of the wire in magnetic field, and on the angle. But in the case of angle, remember, if there is a right angle, then it's maximum possible. If it's parallel, then force is equal to 0. I wrote this here. Wire cannot be parallel to the field lines. Please copy this to your notebooks. I hope that you understand this. Next lesson will be training of this left hand rule. I'm going to create few examples, and your task will be to find the direction of force, or when the force will be given, then direction of the current or magnetic field. Okay, see you next time. Bye.